Have you ever stopped to think about the secret lives inside our gadgets? These little electrical parts doing all the work.
Yeah, the ones that make everything tick, from, say, your car's blinker to huge industrial machines.
Exactly. And today we're doing a deep dive into two really key ones, the properties of inductors and capacitors.
Hmm.
Our source material for this is actually an instructor guide for electricians, focusing on alternating current circuit properties. Pretty solid stuff.
Right, and our goal here, for you listening, is to really pull out the essentials. How are these things built? What do they really do in a circuit?
And why knowing this stuff isn't just, like, academic.
Not at all. It's practical, hands-on knowledge. Crucial if you're working with electricity, designing things, fixing them, or even just curious about how stuff works.
Okay, so let's unpack this. The guide kicks off by saying electricians run into tons of these components, these different kinds of loads.
That's right.
So getting the basics down first before you hook anything up is, well, fundamental.
Absolutely non-negotiable.
All right, let's start with inductors. At the most basic level, what is an inductor?
Okay, so an inductor, fundamentally, it's an electrical part that stores energy, but it stores it in its electromagnetic field.
Ah, the magnetic field.
Yeah. And if you looked inside, you'd basically see wire, usually insulated, wound around some kind of core.
And that core makes a difference.
Big difference. It could be non-magnetic, think air, ceramic, plastic, or it could be magnetic, like iron. And using iron, well, that really boosts its properties.
Gotcha. And people call them different things too, right? Not just inductors.
Yeah, you'll hear coil, solenoid, some reactor. They all basically mean the same thing in this context.
And in diagrams, schematics.
You'll see symbols, different ones for air core versus iron core usually. But interestingly, the air core symbol often gets used as a generic symbol for any fixed inductor. Just something to keep in mind.
Okay, so where do we actually see these things in action? Why does understanding them matter so much?
No, they're everywhere. Seriously. Coils are critical in so much electrical gear.
Like what? Give us some examples.
Well, motors, for starters, they use coils to turn electrical energy into motion, spinning
Right.
things.
Fans, pumps.
Everything. Then you've got transformers. They absolutely rely on inductors to change AC voltage levels. Super important for the power grid.
Can't live without them.
Pretty much. Solenoids, too, those little things that make stuff move, like in doorbells or valves or locks. Relay coils, magnetic starter coils, they're all over control circuits. Think automation. Even older fluorescent light ballasts, the electromagnetic kind, use them heavily. Those are shifting more to electronic now.
Yeah.
And line reactors for VFDs, variable frequency drives. They use inductors for power filtering, keeping things running smoothly. That's a deeper topic for later, maybe.
Wow. Okay, so they're doing a lot of unseen work,
Mm,
constantly managing energy behind the scenes.
exactly. Unsung heroes, like you said.
So we talked about what they are, but the real, the core mechanism is induction, right?
Yeah.
And that's different from inductance.
Yes, very important distinction. The source guide actually highlights this nicely. Think of induction as the process. It's the action, the phenomenon, where voltage gets created because a conductor and a magnetic field are moving relative to each other.
Okay, induction is the doing part.
Right. Whereas inductance is a property. It's something the circuit has. It's that built-in characteristic that makes the circuit, well, oppose any change in the current flowing through it.
So process versus property. Got it.
Yeah. And to get induction, you need that basic physics principle. Current in a wire creates a magnetic field around it, always.
Right.
Now, if that current increases, the field expands. If it decreases, the field contracts.
Okay.
This change, this expansion and contraction, changes the magnetic flux density, basically how concentrated those magnetic field lines are. And here's the kicker. Whenever those moving magnetic lines cut across a conductor, boom, you get voltage induced in it. EMF, electromotive force.
And this is where it gets really interesting, right? Because this is Faraday's law.
Precisely. Michael Faraday figured this out. It's huge. It basically says the amount of voltage you induce depends directly on how fast that magnetic flux is changing.
So faster change, more voltage.
Exactly. The rate of change is everything. It's why generators work, why transformers work. It powers the whole grid, really.
So in something like a generator and alternator, what factors control that rate of change?
Good question. 3 main things. First, how fast it's spinning the rotational frequency. Spin it faster, the conductors cut the magnetic lines faster, you get more voltage.
Makes sense.
Second, the strength of the magnetic field itself, the flux density. Stronger magnet, more lines to cut, more voltage.
Okay.
And third, the angle of cut. You get the most voltage when the conductor cuts straight across the field lines at 90 degrees. Any other angle, you get less interaction, less voltage.
All right, so we have these changing magnetic fields interacting with wires. And you mentioned there are two main types of induction based on this.
Yeah, two key types when the conductors themselves aren't moving, but the fields are changing. First is mutual induction.
Mutual, meaning between two separate things.
Exactly. You induce voltage in one wire or circuit because of a changing magnetic field created by a different nearby wire or circuit. The classic example is a transformer.
Ah, the primary and secondary coils.
Right. Current changes in the primary coil, its magnetic field expands or collapses, and that changing field cuts across the secondary coil, inducing voltage over there. Even if they're not physically connected, just magnetically linked.
Oh.
The guide shows it well. Close a switch in circuit A, current flows, field expands, cut circuit B, induces voltage. Field stabilizes, voltage in B goes to 0, open the switch, current stops, field collapses, cuts circuit B again, induces voltage in the opposite direction.
Clever. And the second type?
That's self-induction.
Yeah.
This is where a coil, or any conductor really, induces a voltage in itself because of the change in current flowing through it.
Wait, it induces voltage in itself?
Yeah. As the current changes, its own magnetic field expands or collapses, and that changing field cuts across the coil's own windings.
Huh.
And this self-induced voltage is really important because it always acts to oppose the change that created it. If the current tries to go up, this voltage pushes back. If the current tries to go down, this voltage tries to keep it going.
It fights the change.
Precisely. Which leads us straight to Lenz's law.
Lenz's law, okay.
Lenz's law basically formalizes that opposition. It says the induced voltage, whether mutual or self-induced, always creates a current whose magnetic field opposes the original change in flux.
So it's inherently counteracting.
Yes. And this self-induced opposing voltage has a special name, counter-electromotive force, or CEMF.
Yeah. Okay.
So current tries to rise, CEMF pushes against it, current tries to fall, CEMF tries to prop it up. It's like electrical inertia. It resists changes in current flow.
So this CEMF, this opposition force, what determines how strong it is?
Two main things. First, the coil's inductance itself. Remember, that's its inherent property to oppose current change. More inductance, more CEM. And second, the rate of change of the current. How fast is that current trying to increase or decrease? The faster the change, the faster the flux changes, and the larger the CEMF.
So inductance and the speed of current change. huh?
Exactly. And there's an equation for it. CEMF equals inductance times the change in current divided by the change in time. L times delta I over delta T.
Got it. Okay, let's loop back then to inductance itself. We said it's the property that opposes current change. How is that different from just plain resistance?
Great question. Resistance R simply limits the steady flow of current. It opposes the current itself, always turning electrical energy into heat. Inductance L doesn't oppose steady current at all. If current is constant, an inductor acts almost like a short circuit, ignoring its wire resistance.
Oh, right.
Inductance only opposes the change in current. It stores energy in the magnetic field when current increases and releases it when current decreases. It's about managing the dynamics, the transitions.
Resistance limits amount, inductance opposes change.
You got it. And inductance is a physical thing determined by how the coil is built. It usually stays constant unless you physically alter the coil.
And its symbol is L. Unit is the Henry H.
Correct. And 1 Henry is defined pretty specifically. If a current changing at 1 amp per second induces 1 volt of CEMF, the inductance is 1 Henry. It connects that cause and effect.
So practically speaking, if I want to build an inductor or understand one I have, what physical things determine that L value, the inductance?
Okay, 4 key factors you can usually control or consider.
Number 1.
The number of turns of wire, usually called N. More turns wrapped around the core, much more inductance. It actually goes up with the square of the turns, so it's a big factor.
Okay, more turns, more L. What else?
Second, the permeability of the core material, symbol, mu. That's how easily the material allows magnetic field lines to form within it.
Like using iron versus air.
Exactly. Iron has high permeability, so it dramatically increases inductance compared to an air core.
Makes sense. Third?
The cross-sectional area of the core, A. A wider core allows more magnetic flux lines to exist for a given field strength, so bigger area, bigger inductance.
Okay. And lastly?
The length of the magnetic path. This is the average distance the magnetic field lines have to travel through the core. A shorter path concentrates the field more effectively.
So shorter path means more inductance. A bit counterintuitive.
Yeah, it seems that way, but think of it as concentrating the magnetic effect. A shorter path means less magnetic resistance or reluctance, so you get more bang for your buck, magnetically speaking, more inductance.
Okay, turns, permeability, area, and length.
And the formula ties them all together. L equals N, N2A.
Yeah.
You can see the number of turns is squared, making it really influential.
And you can see how, like, moving an iron core in or out would change, or maybe effectively changing the inductance.
Precisely. That's how variable inductors often work, or how things like solenoids change inductance when their plunger moves, altering the magnetic path length.
Fascinating. Okay, let's switch gears. Inductors manage magnetic fields and oppose current changes. What about their cousins, capacitors?
Right, capacitors. The other fundamental energy storage component. The simplest capacitor is just two conductive plates separated by an insulating gap.
And that insulator is key, right?
Absolutely. It's called the dielectric, and the schematic symbol usually reflects that two parallel lines representing the plates with a gap for the dielectric.
Now, you mentioned this before, but the types of capacitors are really important, especially this polarized versus non-polarized thing.
Critical. Absolutely critical. Cannot stress this enough. Polarized capacitors, like many electrolytic types, have a positive and a negative lead. They must be connected the right way around in a DC circuit.
What happens if you don't?
Best case, it fails quickly. Worst case, it can overheat, bulge, vent electrolyte, or even, well, explode. It's a serious hazard for both the equipment and potentially for you.
Yikes. Okay, message received. Connect polarized capacitors correctly. What about non-polarized ones?
Those are much more forgiving. You find them with dielectrics like air, oil, paper, plastic, film, mica, ceramic. They can be used in AC or DC circuits because they don't have that inherent polarity requirement.
And they have different characteristics.
Generally, yes. They often have lower capacitance values in microfarads, F, compared to electrolytics of the same physical size, but they can often handle much higher voltages.
Any specific examples?
Sure. Air capacitors, though older tech, were great for tuning radios because you could vary the plate overlap precisely. Oil-filled are used in heavy-duty power circuits. Ceramic discs are tiny but can pack a surprising amount of capacitance.
And the electrolytics, like
Yeah.
aluminum and tantalum.
Right. Those are usually the polarized ones we talked about. They achieve very high capacitance in a small package because their dielectric layer is incredibly thin, formed chemically.
But mainly for DC.
Overwhelmingly for DC filtering and energy storage. There are some special non-polarized electrolytics made for AC, like motor start capacitors, but standard ones are DC only.
Okay, so storing charge is their thing. But where do we use that ability? What are the big applications?
Oh, lots of places. Timing is a big one. The predictable way a capacitor charges and discharges through a resistor lets you create time delays. Think of the delay for interior lights in a car or old-school flashing turn signals.
Ah, okay. RC time constants.
Exactly. Then there's smoothing and filtering in power supplies. When you convert AC to DC, you get this bumpy, pulsating DC. Capacitors act like little reservoirs, smoothing out those bumps to give you clean DC for electronics.
It's essential for almost everything electronic.
Totally. In industry, power factor correction is huge. Inductive loads like motors cause current to lag behind voltage. Big capacitors are used to counteract this, bringing current and voltage back into phase, making the whole system more efficient.
Saves money on the power bill.
Definitely. And another big one is motor starting. Single-phase AC motors often need help getting started. A capacitor is used with a start winding to create a phase shift, generating the necessary rotating magnetic field to get the motor spinning.
Right, those bulky capacitors you see on the side of some motors.
Those are often the start or run capacitors, crucial for torque.
Okay, so let's nail down the core property here. Capacitance. We said inductance opposes current change. What does capacitance do?
Capacitance, symbol C, is the ability to store electric charge. And its main effect in a circuit is that it opposes any change in voltage across it.
Ah, so inductor opposes current change, capacitor opposes voltage change. Nice parallel.
Exactly. It tries to keep the voltage across it stable. If the external voltage tries to rise quickly, the capacitor absorbs charge to slow that rise. If it tries to fall, the capacitor supplies charge to slow the fall. It acts like a voltage shock absorber.
And the unit is the farad.
Yes, the farads. But like we said, a farad is enormous. You almost never see a 1 farad capacitor in typical electronics.
Way too big.
Yeah, so we use microfarads, F millionths of farad, and picofarads, PF trillionths of a farad, much more commonly. The guide has a handy table for those SI prefixes.
So, Similar to inductance, what physical factors determine how much capacitance a capacitor has? How do you build one with a specific C value?
Three main factors again. First, the dielectric constant, kappa. This is a property of that insulating material between the plates.
Like air, paper, ceramic.
Right. It measures how well that material can support an electric field and store energy compared to a vacuum or air, which is rated about 1. Some ceramics can have constants in the thousands. Higher kappa means more capacitance for the same size.
Okay, the material matters a lot. What else?
Second, the area of the plates, A. Just like a bigger bucket holds more water, larger plate area allows more charge to be stored at a given voltage. So capacitance is directly proportional to plate area.
Bigger plates, more C. Makes sense. Third,
The distance between the plates, dis. Here, it's an inverse relationship. The closer the plates are together without touching, the stronger the electric field between them for a given voltage and the more capacitance you get.
closer plates, more C.
So the formula reflects this. C equals CAD. Capacitance equals kappa times area divided by distance.
Got it. Now, the dielectric material has that kappa value, but there's another critical rating for it too, right? Dielectric strength.
Yes, absolutely crucial. Dielectric strength tells you how much voltage that insulating material can withstand before it breaks down and starts conducting electricity, essentially, before it fails.
Measured in kilovolts per millimeter.
Usually, yes. Air might break down at 3 kilovoltmeter, while a material like mica might withstand 200 kilovoltmeter. It's a measure of its voltage robustness.
And that directly relates to the capacitor's overall voltage rating.
Exactly. Every capacitor has a maximum voltage rating, often given as WVDC, working volts DC. You must never exceed this voltage.
Because if you do,
The dielectric breaks down, it gets punctured, loses its insulating property, and the capacitor effectively becomes a short circuit. Poof, game over. Could damage other parts of the circuit too.
and there's a catch with AC voltage, isn't there?
Big catch. The WVDC rating is usually for DC. Remember, AC voltage is constantly changing. Its peak value is about 1.414 times its RMS value, the value you'd measure with a standard multimeter.
So the peaks are higher than the reading.
Right. So if you have a capacitor rated for, say, 200 WVDC, that's the absolute peak it can handle. You should never apply an AC voltage whose RMS value is more than about 141 volts, 1.414. If the AC peaks go over 200 V, even for an instant, you risk breakdown.
Okay, that's a really important safety and design point. Don't put too much AC voltage on a DC-rated capacitor.
Definitely not. Always check the ratings and understand the difference between DC, RMS AC, and peak AC.
Wow. Okay, what a journey. We've gone from basic definitions of inductors and capacitors through how they actually work, induction, capacitance, CEMF, and all the physical things that determine their properties.
Yeah, it's clear these aren't just simple lumps of wire or plates. They're sophisticated components doing really fundamental jobs in almost every electrical circuit.
Managing energy, opposing change.
Constantly balancing things out using those invisible magnetic and electrostatic fields. It's pretty elegant, really, the silent regulators, as you put it earlier.
So maybe a final thought for everyone listening. Next time you flip a light switch, use your phone, start your car, think about that invisible dance happening inside. And maybe consider this. Now that you understand these basic properties a bit better, how do you think this knowledge could maybe spark new ideas, maybe for better energy storage or more efficient power use, or even totally new electrical devices down the road?
That's a great question to ponder. The fundamentals often hold the keys to innovation.
Indeed. Well, thank you for joining us on this deep dive today.
My pleasure.